languages. So let's start now. It's 4 parts. I guess I can start with the introduction, and then Vlad, you can start your talk. All right, so I have the honor today to introduce Vladislav Sorokin from the University of Auckland. So Vladislav is an associate professor at the Department of Mechanical and Mechatronics Engineering, and he is also the head of the Waves and Dynamics Research Group at the University of Auckland. That sounds cool. Anyway, I didn't know there were groups like that in engineering.
Yes, my own group, sorry.
All right, so Vladislav obtained his PhD and Doctor of Science degrees from the Institute of Problems in Mechanical Engineering, Russian Academy of Science in 2011 and 2016, respectively. He held the prestigious postdoctoral position at the Technical University of Denmark, founded by the FP7 Marie Curie Axiom co-fund during 2014 and 2016. In 2017, he was appointed as the lecturer at the Department of Mechanical and Mechatronics Engineering at the University of Auckland, so where we are right now. And in 2021, Vladislav was also invited to act as an official visiting academic fellow at the University of Cambridge in UK, and in 2024 as a visiting professor at the University of Le Mans in France. He published more than 60 peer-reviewed journal articles and registered 2 patents. That's quite impressive. And this includes 50 publications in highly reputable Q1 journals, such as Invited Contribution to Nature and Philosophical Transactions Series A as lead and corresponding authors. All right, so, and today Vladislav will be talking about tailored resonators for broadband reduction of vibration transmission. Please go ahead.
Yes, thank you very much, Marie. Yes, so basically, when I was thinking about what to present today, I thought that basically it has to be on 2 things. So first of all, it has to be relatively heavy on mathematics, on theory. And secondly, it has to be, of course, something related to waves and wave propagation and so on. So in the end, I decided to talk about these resonators for reducing transmission of vibrations in structures, because it's actually directly related to elastic waves and structures, and also it's the mathematics and the theory behind it. It's relatively hardcore, and basically it's based on the works of 2 of my PhD students, Donovan and Ali, and both these students were actually participated in KOZWaves. So probably you remember the talks from the previous KOZWaves. So both are kind of mathematical people who like mathematics more than experiments. Let's go like this. And they are co-supervised with Professor Brian Mays, who is a very famous person in all these vibration transmission problems, and my friend Andrew, who is a very experimental person. Yep. Okay. So basically, a bit of information for people who don't know about University of Auckland. It's a relatively large university based in New Zealand, relatively high ranked, and our department, Mechanical and Mechatronics Engineering. So I'm actually an engineer, not mathematician. So it's a relatively large department. We have like almost 30 academics, and why it's good, what makes our life easier is that if we're asked to make a presentation, then it's not too difficult, because we have typically all academics have a lot of PhD students, so we can just use some of their beautiful works to discuss and present the things. Yep. Okay, so this is about the department, and then what I will be talking about, basically, okay, a bit about background and motivation for this research. So why reducing vibration transmission is relevant. Then basically 2 main things. So the first one is about this force moment resonators. So basically this is just one particular type of resonators or neutralizers that can help us to reduce vibration transmission. And then the second part will be on, okay, what if we have, let's say, many resonators and we want to reduce vibration transmission through the structure, how to position these resonators, how to tune these resonators. So these kind of things. And these 2 topics, these 2 things were actually, okay, related, but not too close. They are within the scope of reducing vibration transmission, but actually generally somehow separated, which I hope is fine. And then I will talk about I will make some conclusions. But everything is very linear, so we don't talk about any nonlinear things in this talk, which is good, because nonlinear means a bit difficult. Okay, so basically, yes, so obviously it's a KOZWavinar, so we talk about wave propagation. So I will be not talking about water waves, although I do a lot of research on these water waves. I will not talk about acoustic waves, sound waves. I will talk about elastic waves. So essentially, waves in elastic structures, beams, rods, plates, and so on. So this is what I will be talking about. Yes, and basically we know, okay, if we talk about waves, then in some cases wave motion is desired. For example, if we're in a music hall or in an opera house, we want to hear beautiful sounds, beautiful music, then this is nice to have waves reaching our ears, but in some cases we don't want to hear anything, we just want to sleep, and then we want to reduce this wave transmission. So I will be talking about this second case when we want to reduce wave transmission. Okay, so basically the general problem is very similar. It is very simple. So essentially, okay, we have a structural element, something like this, and then we have excitation source, some excitation source at one end of the structure, and we don't want to have any vibrations at the other end of the structure. So this is what we'll be talking about. This excitation source creates a wave that starts to go through the structure. So the question how to isolate this part of the structure from this wave. So the best solution, what is the best solution? The perfect solution is very straightforward. Just cut the beam in half. So cut it like this, and then at any frequency of this incident wave, nothing gets here, which is amazing, super beautiful, but it's not really practical. So it will not work. So people try to use different kind of attachments to achieve this vibration isolation. So basically today I will talk about this particular kind of attachment, which is called a force and moment neutralizer. So essentially it's just mass on a spring, a device that has a mass on a spring component, and also this rotational inertia on rotational spring component. So basically two devices in one more or less. So there are a lot of studies when we have just mass on a spring, so something that applies just transverse force on the beam, but not many studies when we have this combined device. But actually, this combined device is very easy to manufacture and build on practice. It's actually very easy. Yeah, so why do we want to have this, something which is called moment neutralizer? Why do we want to have this bottom part? It's because if we consider beams, then we know that actually Bernoulli beam, it has 2 degrees of freedom, displacement and rotation. So basically our force neutralizer, this one, it can restrain the displacement, can apply the transverse force. But the second one, moment neutralizer, it can restrain the rotation. It can apply the moment. And this can be beneficial for reducing the vibration transmission. Okay, and then basically it's not something exotic. So having this kind of neutralizer is not exotic. What is the most conventional way how to have a force neutralizer? It's something like this. So you have a hosting beam, and then you attach this kind of structure, which is basically just another beam with tip masses. So another beam with tip masses, and it's oriented like this. So basically, if you want to go from here to a moment force and moment neutralizer, the only thing that you need to do is just to rotate this device. You rotate it, and then this device will apply not only transverse force, but also the moment on this beam. And this is nice. This is what we want to use. Okay, so basically some of the main things that I will be discussing in my talk today for these force moment neutralizers. So the first case is when we don't have any damping. So then, okay, what are the conditions when we don't have any power transmitted through the neutralizer? Okay, then, okay, in reality, of course, we have some damping. So if we talk about real world, we have to account for some damping. Okay, can we actually still get zero transmission? What about the power absorption? Because if we have damping, it means that some power gets absorbed by our neutralizer. So what is the maximum power and so on? And then finally about experiments, a bit about experimental validation, so that we show that it's all real, and basically these neutralizers are not extravagant, they're all very easy to manufacture and test. But also they are beneficial for reducing vibration transmission. Okay, so we start very simple. This is the most, in this part of the talk, this is the most complicated formula that we have. So just simple formula like this. So on the left, we have the transmission coefficient of a propagating wave in our Early-Bernoulli beam through the neutralizer. And then here we have basically the equation for this wave. So basically we have one component, which is due to the translational, due to this force component of our neutralizer, translational component of our neutralizer. And the second one, which is due to the moment neutralizer. Essentially, they are uncoupled. So basically, you can interpret it like this. What is the wave which is transmitted past the neutralizer? Its original wave, which is incident on your neutralizer, plus additional wave, which is due to this force, which is applied by the force neutralizer, and then additional wave, which is due to this, which is excited by this moment neutralizer. So you have the moment applied on the beam due to this moment neutralizer. So essentially, you have like three waves. You can say that the transmitted wave is just a combination of three different waves. The original wave, the one which is excited due to the force of the neutralizer, and then another one due to the rotation, due to the moment of the neutralizer. Something like this, very easy. Okay, and then you have this non-dimensional translational dynamic stiffness KT and non-dimensional rotational dynamic stiffness of a neutralizer KR. And basically, what are the formulas for this? They are relatively straightforward. So this is the dimensional dynamic stiffness of transverse neutralizer. So basically, the formula is like this: KT is the stiffness of a spring, M is the mass of a neutralizer, omega t is the natural frequency of this neutralizer. And then we want to operate with this non-dimensional dynamic stiffness of our transverse neutralizer, and then we just relate it to the dynamic stiffness of the beam at a given frequency, at the natural frequency of the neutralizer, something like this. So very simple formula, not hardcore, and then we have some non-dimensional parameters. Basically, omega t is just a frequency ratio between the frequency of the incident wave and the natural frequency of the neutralizer. Okay, so yes, and then similarly, what is the rotational stiffness, dynamic stiffness of our moment neutralizer is just given by this formula. So rotational stiffness, rotational inertia of the neutralizer, natural frequency. Okay, and then again, we work with the non-dimensional dynamic stiffness, which is just, okay, we relate this stiffness of a neutralizer to the rotational stiffness at the natural frequency of the neutralizer. Rotational stiffness of a beam at the natural frequency of a neutralizer. And then we get something like this. The most important parameter here is this V, or I think it's V, which is just the detuning. Detuning, basically, because you can have the rotational neutralizer having natural frequency which is different from the translational neutralizer. So they can have different natural frequencies, essentially. It's not a problem even if you do this, you know, even if you implement this device using the simple design that I have shown before. You will probably have different natural frequencies. So it's fine. Okay. So then what do we want to achieve? We want the transmission coefficient for the propagating wave to be 0. So then we just equate it to 0, and then we try to solve it. And then we get very simple relation. Kr minus Kt has to be equal to -1. So rotational dynamic stiffness minus translational dynamic stiffness equal to -1, then we don't get anything transmitted. Amazing. Okay, so then keeping this in mind, okay, what if we have only force neutralizer? Then in order to achieve this, Kt has to be equal to 1. And that, okay, this non-dimensional dynamic stiffness of a force only neutralizer is equal to 1. At what frequency? At a frequency which is slightly higher than the natural frequency of a neutralizer. So somewhere here. Okay, but it's only one frequency at which we can get this complete reduction of vibration transmission. If we have only moment neutralizer, then if we solve this equation, we get that this kr has to be equal to -1. Okay. So at what frequency do we get this? The frequency has to be slightly lower than the natural frequency of the moment neutralizer, slightly lower. Okay. But again, it's only one frequency. At only one frequency, we get transmission is equal to 0. Something like this. So this is fine, not a problem. Now, if we have combined force moment neutralizer, then we can get something like this. And actually, this looks much better than this and this, right? Because here we have like reasonably broad frequency range in which we get like low transmission below 0.5. Okay, and we have two frequencies at which we get 0 transmission. This is for the case when both neutralizers have the same natural frequency. So if natural frequency of a moment is equal to the natural frequency of a transverse neutralizer, then this is the case. So we have basically two frequencies at which we don't get any transmission of waves. So the first one is obviously when the frequency of a wave is equal to the natural frequency of a force neutralizer and moment neutralizer, because essentially our beam behaves like it looks like it has a fixed end, because basically at this frequency there can be no rotation and no transverse motion of a point of attachment of a neutralizer. And then we have another frequency in which we don't get any vibration transmission, but this is a phase dominant solution, something that we call a phase dominant solution. Why it's phase dominant solution? Because we actually get some vibrations of a point of attachment of a neutralizer, and then we have two waves which are excited, one by the force neutralizer, another by the moment neutralizer, okay? But they actually interfere with the incident wave, so that in the end you get 0 transmission. Something like this. Okay. So basically the key thing is here. So okay, we have incident wave, and then we have one wave due to the moment applied by the neutralizer, another due to the force applied by the neutralizer, and in the end we want these two to combine to cancel the incident wave, and then we don't get any transmission. Okay. So basically this is in detail discussed in this paper, and basically what we show is that yes, it means that in many cases, this force moment neutralizer can be better than conventional force neutralizer in terms of the force, in terms of the bandwidth of vibration reduction, vibration transmission reduction. But we can also get something like this, actually. We can get that actually having this additional component, the moment component, is very bad. So basically, this is one of the interesting things to mention is that, okay, typically we think that, okay, if we have a force-only neutralizer, then the larger the mass, the better. Because then we get a larger reduction in the bandwidth of reduction of vibration transmission. In this case, actually, if we not properly tuned our device, if there is some particular value for this parameter V, which is the detuning parameter, the difference between the natural frequency of the force neutralizer and the moment neutralizer, and we didn't tune it properly, then actually we can never achieve vibration transmission equal to 0. We can actually get something like this. And why do we get something like this? It's very simple. It's because the wave, we have these three waves: incident wave, the wave by the force neutralizer, the wave by the moment neutralizer. We just combine together to get actually in the end a wave that has the same magnitude as the incident wave. So this is a wave interference effect, unfortunately. So just something to be aware of. Okay, so yes, okay, so now actually in my presentation I focus on the things which maybe but it's just interesting. Something that I call cool things. So maybe if they're not cool, it's fine, but it's something that I feel cool. Maybe even if something is not working, I still want to present just because it's interesting. So if something is not working, let's say here, clearly the device is not working, it's not because we're stupid, it's just because it's interesting, okay? Okay, and then we have some damping in the structure, obviously in the real world. So if we want to do some experiments, if we want to implement this device in reality, we need to account for damping. And basically, the typical way how to do it is just to account for structural damping. So we account for structural damping, we assume that translational stiffness has imaginary part and rotational stiffness has small imaginary part. Typically, it's relatively low. With imaginary parts, structural damping ratio for them is relatively low, so maybe less than 1%. Okay, so what do we know about force-only neutralizers? So if we have only force-only neutralizer, so in case when we don't have any damping, we can get vibration transmission equal to 0. But if we have some damping, especially if the damping is relatively large, then we can never get T equal to 0. So we basically transmission cannot be equal to 0. We always get something going through the neutralizer. Something that we know. And this is probably not good. Okay. If we want to talk about the combined force and moment neutralizer, then we need to account for the, we need to take into account the power absorption because it's sort of important. And then we also see that actually, so okay, this is the power absorption, the power absorbed by our neutralizer, and we see that actually, yes, there is some component due to the force neutralizer and some component due to the moment neutralizer, and they again uncoupled, which is actually simplifies the analysis a lot. And then what do we see? If we start to play with the tuning parameter, so we start to play with the natural frequencies of this force and moment neutralizers, we start to play with them, we start to increase this detuning parameter from negative to positive, and what do we get? So black line corresponds to the case when we have small damping, let's like maybe 0.5%, and this dashed line to the case when we have considerable damping, I think around 20%, or maybe even 30%. So, okay, in this case, this is something that we can easily understand. Okay, we add more damping, so we sort of remove all these peaks. So we make the peaks smooth, and then we get something like this. This is fine. Here, this is also understandable. We cannot get the very small transmission. We get transmission which is slightly higher. But here, what do we get here? This is very surprising, very strange. And actually, this is something what I want to show. We get something like this. So, okay, if we don't have any damping, then actually the transmission, we have considerable transmission through the structure. We get this black line. But now we start to add a lot of damping, and actually we can get zero vibration transmission. So why is that? Because of this interference effect, because of the waves. So basically the thing is that what is happening if we have very, very small damping, we have these two waves which are generated by force and moment that combine together to give us some transmission. But if we have some damping in the system, in this neutralizer, then these resulting waves are smaller, and in the end they cancel each other. Something like this. Okay, and then we come back as soon as we further increase the tuning parameter, we get something like this, something normal. But I think this is very cool. So damping can help us to reduce vibration transmission, the magnitude of vibration transmission, which is very nice. And if we talk about the power absorption, which is also interesting, then the first thing to mention is this. So, okay, so first of all, we can actually get zero transmission. So no power, no energy will be transmitted by combined reflection and absorption. So some power will be absorbed. So this is shown by this black line, and some power will be reflected. And here, when we touch, we get zero transmission in this frequency range. And this is the moment component, and this is the force component. So actually, yes. So in the end, we can get zero transmission, and then some power will be absorbed, some power will be reflected. The question, can we get that all the power is absorbed? And the answer is yes. We actually can get something like this. So again, black line is the total power absorbed, and it can be 100%. And again, this is something cool because we can potentially use it for energy harvesting applications. If we use force-only neutralizer, we can never get something like this. But if we use this, then we can get it, and this is cool. So you're not only isolating vibrations, you actually can potentially harvest all vibrations. And then basically, if we talk about the band wave or the power absorption, then of course having this moment component and the force component can be beneficial because the total power absorbed can be something like this. So we have a reasonably wide band wave of this power absorption, considerable power absorption. Okay, so a bit on experiments because I'm engineer, so in order to believe in something, we need to do experiments. So the first question, okay, if we actually want to do this, if we want to use this resonator, then can we use this simple mass spring model to describe the behavior, because this is what we have been doing. Maybe we need some high order terms or something. What about some practical restrictions and differences between theory and experiment, something that we need to discuss. And finally, how to design a neutralizer. So this is about experiments. So this is our experimental setup. So something very simple. So we have a excitation source. We have sound boxes to absorb the waves which are going here and here. We have accelerometers to measure to estimate the transmitted waves and reflected waves and so on. And then we have our neutralizer. Okay. So this is our neutralizer. This is the force-only configuration. If you rotate, you get the moment. So essentially, this is how it looks like. Essentially, due to the fact that we have some point of attachment and so on, it's actually not just a mass on a spring. It's actually a mass on a spring and a mass. This is fine, not a problem. And then if I count it in our calculations, then we get something like this. So basically, black line is experimental result for the transmission. And then I think dashed line is the simplified theoretical model. Dotted line is a bit more advanced theoretical model, but basically we get very good agreement. And if we can consider force moment neutralizer, then we get something like this. So experiments are shown by this black line. So we have two frequencies at which we get very small transmission, which is good. And then, unfortunately, the theoretical predictions are shown actually by this dotted line. So our original theoretical predictions, they were shown by this dotted line. So this was all very nice. And then we have seen this, the black line, when we were somewhat disappointed, because clearly it's not a good agreement. Why we have this bad agreement? Because actually there is additional flexibility, additional rotational flexibility in the point of attachment of our neutralizer. So if we account for this rotational flexibility, we need to adjust slightly the natural frequency of this rotational neutralizer when we get this dashed line, and then we have perfect agreement, everything is fine, everyone is happy, amazing. So in the end it works. So in the end, basically we have good agreement, and what we have predicted theoretically makes some sense. Okay, so basically some concluding remarks on this part of the talk. So the first thing is that okay, obviously, if we work on neutralizers and reducing vibration transmission, then two main things. The first one is about zero transmission, and the second one is about bandwidth or vibration transmission. So if we talk about zero transmission, then okay, we have found frequencies of zero transmission for the force moment neutralizers. If there is no damping, then we have two frequencies. And actually, we have shown that if you use damping, so if you properly tune the damping and with neutralizers, then we can still get zero transmission, which is actually very cool and very much opposite to force-only neutralizers. And then in terms of bandwidth, we just basically shown that, yes, actually, if we use both force and moment components, we can increase the bandwidth of vibration reduction because we have two, and it doesn't matter is it damped or undamped, we get increased bandwidth for vibration reduction. Okay, so this was the first part of my talk. A lot of details are in these pages, if you're interested. So now we continue to the second part of the talk, which is related to, luckily again, everything is linear, nice and easy. So the second part is related to, okay, now we're becoming a bit more serious. So what if we want to have many resonators? So basically, we want to have not one resonator, but maybe we want to have many resonators or neutralizers or absorbers. And also another thing is that in reality, of course, we have boundaries. So we have boundaries of the structures. So we need to account for the boundaries of our structures. And still, we are talking about this reduction of vibration transmission. Yes, so we want to get broadband sound and vibration isolation in finite structures. Now the structures are finite. And the solution is with metastructures with many tailored resonators. Okay, and then, okay, what are some of the definitions? So what do we mean by tailored resonators? They are not periodic and non-identical. So we just want to properly design these resonators. We don't constrain them to be periodic or identical. We want to have a procedure how to design these resonators and how to tune them and how to position these resonators if we have a structure. Okay, and some of the definitions. Okay, here in this kind of part of the talk, I will be talking about not transmission, but transmissibility. And what does it mean, transmissibility? It means that, okay, we have a point of, let's say, input, the point of input force, and then we have a point at which we measure the response. And basically, we have some amplitude, some displacement here, some displacement here. So the ratios between these displacements gives us the transmissibility. And basically, if we consider this graph of transmissibility with respect to the frequency of the wave of this force, we basically get, okay, there are some amplification bands in which transmissibility is larger than 0. And then there are some, sorry, actually it should be larger than 1. Here it's in dB, sorry. So this is in dB. This is just normal, but this is in dB. So here we talk about dB. So TR is larger than 0 dB, larger than 1. Here TR is smaller than 0 dB, smaller than 1. Then we have attenuation. So basically, if vibrations at the point of response is smaller than vibration at point of excitation, then we have some attenuation. If it's larger, then we have amplification. Something like this. Okay, so how do we analyze the structures? It's actually not too difficult. A bit of equations, but it should be fine. So, okay, we have a structure with many resonators. We have this some boundary conditions. We can have some forces applied at different points of the structure. It doesn't matter what we do. We consider, let's say, a certain segment of a structure between two discontinuities. It can be either resonators or boundaries. And then we consider this kind of segment. And then basically what we do, we just, okay, relate the wave amplitudes on the segment. So, okay, if we have a rod, then we have a simple relation. And then we also account for the, okay, what is happening with the wave as it passes with the discontinuity. Let's say passes the resonator. So we need to use the transmission and reflection coefficients of the resonator when we determine the deflection of the structure at any point. Something like this. So it's not too difficult. So if we consider each segment, then we have 4 wave amplitudes and 4 equations for each segment. So wave propagation equations, very straightforward, that relate with wave amplitudes here. And then wave reflection and transmission equations, something like this. So they depend on reflection and transmission of each of the neutralizers. And then we can have some forces. This is for the rods. So this is for the rods, not for the beams. It's also similar. I will discuss it a bit later. This is for the rods. So everything is a bit more simple. Okay, so key points, number of equations equals the number of unknown wave amplitudes. We can get analytical expressions. Matrix formulation is possible, so we can do it very easily. And then we don't have actually any restrictions on the type of discontinuity, so it can be any sort of resonators as soon as everything is linear. And we also don't have any restrictions on the rod properties between these discontinuities. So actually, we can very easily apply this approach if we have, let's say, some variation in the properties of this rod, let's say, from one segment to another and so on. It's not a problem. This method works. Okay, and then, yes, reflection and transmission coefficients. This is something that we need to use. So this is the reflection. This is for a rod. So we have a rod, and then we have a mass, a resonator with a mass and spring and damper. And then, okay, this is the reflection coefficient. It depends on the frequency, on the natural frequency, and so on. At the mass ratio of this resonator to the hosting structure, at the damping ratio. But essentially, we know it. So we can get this reflection and transmission coefficients, and then we can actually put them here and solve for displacement of the structure at any point. It's not a problem. Okay. So example analytical expressions. Okay, just one undamped resonator, we get something like this, and then transmissibility will look something like this. So it's basically just, it's all possible. For one resonator, we get this sort of equations. If we have 10 resonators, we get more complicated equations, but it's not a problem. We can do all this. We can find deflection at any point of our structure. Okay, so then this is easy, this is fine. So basically, Now we talk about some practical results. So, okay, so what about if we want to use, if we want to reduce vibration transmission using these resonators? So what is the conventional approach? The conventional approach is that we try to, as I said here, engineer attenuation band. So we have a hosting structure, something like this. It's shown by these dotted lines. And then we have some peaks in transmissibility. So let's say we have this peak in the transmissibility, and we want to reduce it. So we want to attach resonators so that we reduce this peak. It's very easy. We just use the conventional approach. We just attach it, probably in some way in the antinode for this given frequency of excitation, and then we get something like this. If you want to make it broader, you just target this frequency. Now with a second resonator, and then you get something like this. And then if you want to make it even broader, you target now maybe this frequency, and then you get something like this. Okay, so your resonators are not periodic, they are non-identical, but you can get a very broad band, frequency band in which you get small transmission. So this is kind of boring, not interesting. This is conventional and presented in this paper. So this is not too fun. But the cool thing is the one that I want to discuss right now. So basically, it's called super attenuation bands. So this is something cool. If you have something which is called super, then probably it's interesting. And it wasn't called super by us, it was called super before. So basically, first of all, we start with the following. So, okay, let's say that something that we know from year 3 courses in dynamics. We know that if we have a single degree of freedom system, then it has a resonance. Okay, it has a resonance, and then if you excite it at this resonant frequency, you get a large response. So this is our red line. Then if you attach an absorber, just a mass on a spring, essentially this is what we do here in our research. Then, okay, the system becomes 2 degrees of freedom. So instead of 1 resonance, you get 2 resonances. But the good news is that if you tune it properly, your vibration absorber, so you tune it to the natural frequency of a machine, and then you get a huge reduction at the targeted frequency. Okay, so this is how it works. You get reduction, let's say you target this frequency, the natural frequency of a hosting structure, of a hosting system. If you attach this absorber, you get huge reduction at this frequency, but you get additional frequencies in which you get large response. And then if you want to increase the bandwidth, you just need to make your mass M2 very large. So mass of vibration absorber has to be large. Then you increase the bandwidth. Okay, so this is what everyone knows. But can we somehow do something that we don't get this additional amplifications? And the answer is yes. So this is called super attenuation bands, and this is something that I illustrate quickly on rods. So how do we do it? First of all, we consider just our resonator itself and try to define the dynamic stiffness. So if we consider dynamic stiffness of this mass on the spring, then we get something like this. This is the equation. And then what do we see? We see that this is for rods as a start. We see that, okay, if the frequency of excitation is smaller than the natural frequency of this mass on the spring, then essentially it behaves as a mass. So effectively, this is just a mass attached. And then if we consider, okay, frequency is higher than the natural frequency of this mass on the spring, then essentially it's like a stiffness. So this thing behaves as a stiffness, okay? And this actually was discussed by Brennan in 1998. Okay, so this is all known. So below natural frequency, it behaves as a mass. Above it behaves as attached stiffness. But this is amazing because basically it means that if we attach our resonator to the structure, then below the natural frequency of this resonator, we will get that all the modes, all the amplifications will be shifted to lower frequencies, right? Because we added mass. We sort of added we attached mass to the system. So all the natural frequencies of the system will go down, will go lower frequency. And then at the higher frequencies above the natural frequency of our attachment, all the frequencies will go higher. All the natural frequencies will go higher. So this is dashed line is the original system. And then this black is with the added resonator. Okay, but then what about the resonant? What about the resonant amplification? We need to kill it somehow. So how do we kill it? We just attach it. First of all, we design it so that the natural frequency of this attachment is actually coincides with this frequency, the frequency when the structure at the point of measurement is not really moving. Because then, if it's not moving, then essentially the resonator will not be moving. So basically, you attach it at the point at which at this frequency the structure is not moving, right? So the natural frequency of a resonator is equal to the frequency of a wave of this at this particular excitation frequency, and then at this particular excitation frequency, the point of attachment of a resonator is not moving, so it's not moving. So the resonator at this frequency, at which it's actually tuned to work, is not doing anything, and it means that you don't get this amplification. So you shift the frequencies, but you don't get additional amplification because the resonator is not actually working as a resonator. Okay, so basically placing a resonator at a nodal point of a given force vibration mode of, let's say, a bare rod, the structure that you want to reduce vibrations, you can get a wider or super attenuation band. So something like this, and this is how it looks like. So, okay, this is our original structure, and then you attach it in this nodal point of your structure, and then you get something like this. So you considerably widen this particular attenuation, you widen this attenuation band, essentially. So it's all good. Okay, and then basically, okay, when the problem is that, you can say that, Vladislav, this is all very good. We can call it super. Indeed, you get this amplifier, you get this increase of the attenuation band. This is very cool. But the problem is that even if you don't have your resonator, the structure is not moving at this frequency. Okay, you shift these peaks, this is cool. But what if we want to reduce vibrations at this particular frequency? Maybe at some particular frequency, maybe this peak frequency. Can we still do something? And the answer is yes. But then what we want to do, we need to combine different vibration attenuation mechanisms. So essentially, how do people do it conventionally? So we have, let's say, resonators that tune to peak frequencies in your transmissibility. So let's say 2 resonators, you tune them to this peak frequency in which you get large response. You put them in the anti-nodes at this particular frequency, and then you get anti-resonance. So you get a lot of reduction. So what we proposed is something like this. So the first resonator, we follow this conventional approach. So we tune it to the peak frequency because we get this reduction, we get the node. And then the second resonator is tuned to the same frequency, but positioned not at the anti-node, but at a nodal point. And then we can expand, basically by the second resonator, we can expand. So the first resonator creates the attenuation band, and the second resonator expands this attenuation band, essentially. And this is the comparison. So, okay, so this is example. So dotted line is the bare rod, then dashed line, this line, is one resonator placed at the anti-node. So, and then this dash dotted is when we have 2 conventional resonators, so both placed at the anti-node, and then this black solid line is using our method. So clearly we get a much wider reduction of vibration transmission, which is cool. 42% wider attenuation band, amazing. Okay, so basically for beams it's very similar. We have a bit more, we now have 8 equations instead of 4 equations. It becomes all matrices and so on. But this is not too bad, so still we can, it all works. And basically this is just example. So I don't have too much time to discuss, unfortunately, but this is one example. So here basically, what can we say? We see that this dotted line is the original structure, is just the bare structure. And then we attach a resonator. The natural frequency of the resonator is this one. The tuning frequency at which it can reduce vibrations, to which it's tuned to reduce vibration, is this one. And basically this is the conventional approach. So okay, you target this amplification and then you get this sort of band. But then if you do it like we suggest, so you put it at the nodal point and target some different frequency, then you get, instead of this attenuation band, you get this attenuation band. So you can get a lot of attenuation. Essentially, so it also works for beams, essentially. Okay, this is not important. This is another example, transmissibility, how we do for the beams. So we can expand the transmissibility for the beam. And then finally, experiment. So it's not crazy. This is all works. So this is all very easy to reproduce in experiments. So this is the case when we have 3 resonators, but this is a bit hardcore. So I need to discuss it in details. And I don't have time, so I will just focus on the case of 1 resonator. So basically, first, this is just 1 resonator, just a beam with 2 tip masses. Okay, we just get the dynamic mass of this resonator. It's given by this formula. We compare this formula with experiments. We get perfect agreement. So we know that, yes, this is indeed the dynamic mass of this resonator. And then we try to play with this resonator to get this super attenuation band. And actually, we get it. So basically, this dashed line is the bare beam. And then we tune our resonator, position it at the nodal point, and then we get this black line. So we can indeed get this super attenuation band experimentally. And actually, you can say that you need to tune everything perfectly. No, if you actually slightly mistune your resonator, you get something like this. So you get some small notch here, but it's not important because you get a lot of reduction anyway. So basically what I want to say is that this approach is actually very robust and it's practical. It's not something crazy. Okay, so this was for this part of the talk. So we basically use this wave approach to determine displacement and transmissibility in rods and beams with discontinuities. We can achieve very broad attenuation. We can get the super attenuation bands. We don't introduce any additional resonances. And actually, experimentally, we showed that it works. So it's all true. We can get super attenuation bands. Okay, so this is basically it. Maybe the end was a bit rushed. Sorry for this.
Thank you, Vladislav. All right, we have like 5 to 10 minutes for questions. So please raise your hand if you have any question for Vladislav. And don't forget to unmute yourself. Any questions? Oh yeah, Amin, please. Yeah, don't forget to unmute yourself.
Sure, sure. Yeah, thanks, Vladislav. Very interesting talk. Just have a question regarding the last part because it involved experiments. So what would be the challenges if you would look at bigger scales? So, let's say you want to apply this to wind turbines. So what are the challenges there, and would the linear or simplified approach, which is of course valuable, is a good starting point, of course, would it be still valuable, or how would you tweak this, or how would you integrate nonlinearities and particularly, let's say, wind excitation?
Yes, so this is actually a very good question. And to be honest, so the student has submitted his thesis, and one of the examiner comments was exactly like on this.
It wasn't me.
This seems to be very nice, but actually, if we talk about practical applications, how to make it like real for larger structures and and so on. So to be honest, basically, okay, in the lab it works, so it seems to be fine. But obviously, in this wind turbines, you have to the answer that we prepared for examiners that you just need to try it for wind turbines. And luckily, the guy is in Denmark now working in a wind turbine company, so he can maybe persuade to try this approach, and then just see how it goes. So realistically, it's difficult to say whether it will work or not, because to be honest, my practice shows that there are so many things that work in the lab, but not work in the practice. So
of course,
unfortunately,
right? Yeah.
I cannot say that I'm too positive about this. I think it's cool to show that there is this kind of opportunity, and we can do the super bands, super stop bands, super attenuation bands, but like for real practical applications, I don't know. I'm not sure.
It's a good starting point. Yeah, sure.
Yes.
And think of floating turbines. They're also great.
Yes,
program.
but actually, I will have from next year. I already signed up for one PhD student who will try to use this thing for bridges.
Oh yeah.
Because basically, and then we will talk about the wind-induced vibrations and all these kind of things. So we will see what will happen with this guy, because basically what we see is that if we talk about this vibration transmission problems and these kind of things, then of course, like metro things, like metro structures with railway tracks is a very nice application. Wind turbine is also a very nice application, but also with bridges, they're also very good application.
Sure.
So, and in New Zealand we have some wind, so we will see what will happen.
Yeah, it's particularly, I think wind is particularly, is of particular interest in Okinawa, and especially we have typhoons blowing from time to time. So
Yes,
I'll be keep following the research. Great stuff. Thanks.
thank you.
Do we have other questions for Vladislav? Anyone else?
Any grilling questions? I always like grilling questions.
I can ask you a question, Vladislav. I'm not sure if it's going to be a grilling one. Yeah, nice talk. Go back to the first part. All your theory is 1D, correct?
Yes.
And I think one of the really nice aspects is you get this decoupling between the two terms.
Yes.
That allows you to design your attachments in order to get the zero transmission of what you want. So, boring question, to 2D. Would there be a similar decoupling in there?
So basically, I think that, to be honest, if you ask something like this about the second part of the talk, then it will be much more easy for me to answer. Because for the second part of the talk, definitely we see how to do it for 2D. Because basically, you know, for 2D, is if it's a plate, still we talk about some particular point of response that we want to study. And then we use these nodal things and so on. So it will work for 2D. So this thing will work for 2D. This one, I think I don't know, to be honest, I'm not sure whether we can still do it, but I think we can try. So
I guess my thinking comes from water waves, where you have relations which correspond to the different modes of motion, and I was just wondering if there's an analogy here. I'm also aware that Paul Martin wrote a paper a few years ago in which he generalized those relations to elastic bodies. You've got something a bit different.
Yes.
Just wondering if there's something universal going on. And I realize that you can't characterize reflection and transmission in the same way in the 2D problem.
So I would say that basically, if we do something like, if we have a resonator which is symmetric, like axis, like completely axis symmetric. So basically it's like a circle, and then we have this mass on the distributed just along it. So basically like a circle and then mass on the edges. Then I think that maybe we can try to do it. So it has to be symmetric. So okay, the force component will be fine. But when the rotational component, it has to be the same, doesn't matter what is the direction of the incident wave. You know, so we have a plate, and then it doesn't matter what is the direction of the incident wave, we have the same moment. Then I think it should be fine. But if we have something like this, then it will be too complicated. Because it will depend on the direction of the incident wave. It will be very unpleasant to do. So I wouldn't do it myself. But maybe we can try it actually. Maybe for the symmetrical one, we can try. So this is interesting.
All right. Well, it did turn out to be a nasty question, so apologies for that, but that's what you wanted.
Yes. It's a good question, actually. Something for us to think. But again, I hope that someone will ask about plates for the second one, because it's relatively easy. And actually, the student, for his defense, he prepared this answer. So it's good. I like this sort of things when everything is sorted. Yep. Sorry. Okay.
All right. Do you have a last question for Vladislav? Otherwise, well, it's already almost 4, so we will thank Vladislav the last time for his talk. Thank you for joining today. Thank you for everybody who also joined the meeting today. And well, I don't know when we will have the next meeting, so just check your emails for news.
Thank you very much.
Thanks, Vladislav. Thanks, Marie. Thanks, everyone.
Yes. Thank you so much.
See you next time.
See you. See you.